Hello, everyone. It's a very big honor to be here, and thank you very much for hosting me. It's very exciting to be giving this talk in front of such an audience. So the talk I'll be giving today is affordable analytics using hardware-accelerated flash storage. And that's a mouthful, and I'll get into what that exactly entails in a little bit. Before I actually get started on anything, I'm going to just give a very high-level overview about what the entire talk's going to be. It'll be about cost and power-efficient analytics using FPGA-based hardware accelerators, coupled with processing in flash storage, and a little bit of magic sauce, which will be the most interesting, hopefully the most interesting part of this talk. So this is the basic process that I will follow. There, I showed you everything. So we need to build efficient systems by Captain Obvious. And what does efficiency mean? And with the worry of getting a little bit too general, a little bit of beating around the bush, I'll go into a little bit of analytics about where the cost goes in a data center. There's a lot of things that cost money when running a data center, but everything on the left here, we can't, as engineers, we can't really do anything about. The cost of building data center infrastructure, the running the infrastructure, and things like that. What we can do is deal with the cost of servers, of which most of the cost is, well, a big part of the cost is on the right, how much the CPU costs, how much the memory costs, and everything else is a little bit. I think these numbers are from Google numbers, at least the ones on the left, from 2017. And of course, another thing that we can do something about is the amount of power consumption. I guess the big takeaway from these two charts is that we care a lot about power consumption as power-efficient computing to bring down cost. But still, in the scale of data centers and scale of anything, actually, still the cost of hardware itself is possibly even a bigger factor in actually doing total cost of ownership. So let's look at power. And again, with a little bit of fear of beating around the bush a little bit, I just like to show this kind of funny slide. So back in 2016, the Department of Energy requested from the academia and industry that they want an exascale machine by the year 2020, back in 2016. Exascale machines, by definition, needs to process a lot of numbers, floating point operations per second. And using technology back from 2016, this single warehouse scale machine would have consumed 200 megawatts of power. And to put that into a little bit of perspective, how large that number is, this photo is from the MIT Research Nuclear Reactor. It is the only nuclear reactor located in a residential area for some reason. I lived in that red building in the back. And this thing, of course, it's a research reactor, not for actual power consumption, but the total output of this facility was 6 megawatts. So, I'm twisting the numbers here a little bit, because if we compare the numbers against the biggest nuclear power plant in the United States, then, before I get into that, the technology has come a little bit of a way since 2016. Now, Cray is actually building this exascale cluster called El Capitan, which will be done, I think, in 2021. And using 2019 technology, this machine is projected to consume 60 watts of power, which is a big way down from 200. So we've come a little bit of a way. And again, like I said, I'm twisting the numbers a little bit, because if we compare ourselves against the biggest power generating facility in the United States in terms of nuclear power, that number is pretty high. So to give a little bit of number that feels a little bit closer to home, the total residential power consumption of San Francisco is 168 megawatts, as according to 2018. So we see the kind of numbers that are being dealt with here. And where does this power come from? In a typical data center, according to, I forgot which data center this was actually from, a majority of the power goes to cooling. And after cooling, majority of the power goes into server and storage, so the actual IT stuff that's going on. But of course, if we reduce the power consumption of CPUs and memory and thermal, other heat-causing things, then the power consumption of cooling will go down naturally. So reducing the power consumption of computing hardware has more effects, I guess, larger effects than just that 26% chunk slice of the pie. And within a server, and this again is from the 2017 Google numbers, 61% is being used by CPUs on the right, 18%, which is the second largest chunk, is consumed by DRAM on the left. And this is from a book that was published by some engineers at Google from the third edition. And what's interesting, according to the third edition book, is in the first edition, when the numbers were first gathered, the total power consumption of memory and CPU were shifting so that the DRAM power consumption was almost as much as CPUs. But I guess apparently after that, either the DRAM power consumption has become a little bit more efficient or the CPU power consumption has become larger. But the state of things right now is that there's CPUs and memory is the largest power consumption culprits. So this is where my research comes in. I want to reduce the cost of servers of doing analytics, of which CPUs and memories take up a significant amount. And I want to reduce the power consumption of the same analytics, of which CPUs and DRAM take up a significant amount. And the two tools I've been working with, and I will continue to work with, first is for CPUs, FPGA accelerator offloading of computation, and also replacing a lot of memory with PCI-attached fast flash storage. And I will get into how and what these are shortly. For those of you who are not quite familiar with FPGAs, FPGAs stand for Field Programmable Gate Arrays. They are IC chips that can be configured to act like any circuit that you want, provided you have enough on-chip resources on the FPGA. The optimized chip, the configured chips can be optimized to whatever application that you have. So typically, they have very high performance, very low power. And to put that into sort of context compared to other technologies, here's an anecdote and application, Bitcoin mining. In Bitcoin mining, these are a number from some people that collected these. Typically, and this pattern continues for most other applications as well. FPGAs, you can see in the middle, the performance is typically similar to the overlap with FPGAs or totally optimized ASIC chips, while the energy efficiency is typically significantly better than GPUs. So most of the time, the rule of thumb is that when you compare GPUs and FPGAs together, in performance-wise, they do pretty similarly depending on the amount of effort that you put in, while the power efficiency is typically better with FPGAs. The downside of FPGAs is that the effort that goes into designing your application is quite high. No thanks to the tools and tool chains and application development infrastructures that are not quite there yet. But since with Moore's law kind of slowing down and us running into the power wall, et cetera, a lot of companies are actually more interested in this technology in the past couple of years. Amazon has FPGAs in their cloud. Microsoft has FPGAs in their cloud. Baidu has FPGAs in the cloud. I think Huawei also has FPGAs in the cloud. So it's getting bigger and bigger. So this is good. I mean, if we put in the effort to do something on the FPGA, it gives us performance. So that's kind of simple. So we'll go into the next technology. So when we deal with large-scale data analytics, typically when we have a lot of data and the algorithm requires fine-grained random accesses into data, which is typically the case for complex algorithms, we need to put them on DRAM as opposed to storage because DRAM is faster than storage typically. The problem becomes when the data set becomes large, terabytes, multiple hundreds of terabytes in size, then you need a lot of DRAM. And the cost of that is kind of high. For example, as of right now, if I buy a terabyte of DRAM off Amazon, it would cost me upwards of $5,000. And the memory subsystem will consume, I say more than 200 watts, but something more like 300, 400 watts, just the memory. The goal would be to replace all of that, or at least a significant portion of that, using flash storage, which is significantly cheaper. I think on Amazon right now, if I buy a slightly high-end PCI-attached SSDs, it would cost me about $300 per terabyte, less than 10 watts of power, 6 watts of power. And even better, if I can just use an even slower SSD, it would be great because it's much cheaper, much less power, but we'll see if that's possible. The problem is a drop-in replacement of using SSDs instead of memory causes a sharp performance decline. And there are many reasons for this, some obvious, some less so. First is the overhead of data movement. This chart is from a research group at UC San Diego. There's a lot of small text here, but the big takeaway from this is if we have a lot of SSDs that have a lot of aggregate bandwidth, the PCIe root complex performance on the CPU side will become a bottleneck. For example, they're talking about slower generation SSDs, even 2 gigabytes per second, but if we have a lot of them, we will saturate and sort of overflow the performance of the PCIe root complex on the CPU. Of course, every generation CPU has a faster PCIe root complex, more lanes, but every generation of SSDs are going to be faster as well. And on top of that, the internal bandwidth, as Samsung folks, you probably know this better than I do, the internal bandwidth of storage devices, or the peak internal bandwidth at least, is typically faster than the PCIe link that it has. That was the first challenge of doing complex analytics using storage instead of memory. The second challenge is the overhead of random access. Of course, we have the bandwidth differential between flash and DRAM, order of magnitude difference, and larger performance gap in terms of latency between flash and DRAM. But the bigger problem I've experienced when trying to do analytics on storage is the problem of access granularity. Flash access is typically done in pages, 8K, 16K, 4K, depending on the technology that you have, whereas DRAM is accessed in cache lines. Of course, there's intricacies that go on inside DRAM as well, but this is a simple enough comparison to understand. The problem is when your algorithm requires very fine-grained accesses, and this is typically the case I've experienced when you're dealing with interesting complex algorithms, then you waste performance by not using most of the data that you actually load from storage, which has its own overhead. For example, if you load 8 kilobytes of data and use just 8 bytes of it, then your read amplification results in in the effective bandwidth going down by 1,000-fold, which is irredeemable. It's going to kill your performance. So the big goal of my research so far in the past couple of years has been to solve these two issues by putting these two technologies together. So the first half of the solution, the first half of the two solutions that I'm going to present is near storage computing, near storage FPGA acceleration. Which is the solution to the first problem, the problem of data movement. For example, if we have a fast internal bandwidth between flash storage and FPGAs, then if we can do computation inside the FPGA itself, high performance, low power, and we can just send the data to the CPU, then we save a lot of PCIe bandwidth. And of course, if you have multiple SSDs, the benefit is compounded. And of course, when we need to have data movement between the data in multiple storage devices, it would be beneficial in terms of bandwidth saving to have direct communication between the SSDs themselves. So this idea of near storage computation is not anything very new right now. It's one of the slightly hotter field of research. But back in 2013, when we first started getting interested in this idea, there wasn't a platform out there for us to do this kind of research on. So it required us to build our own platform. So this is the Blue DBM flash card that we've built from the PCB level up back in 2015. It had 3 requirements when we were building it. Each card has half a terabyte of flash. 3 requirement was, first, we wanted to be able to modify the internal flash management, things like we wanted to be able to change the flash translation layer, get rid of it if you want, et cetera, et cetera. That's why we have a small FPGA on the storage device itself on which we implemented the controller. The second, The second requirement was we wanted to have the dedicated storage area network between the storage devices themselves. And I think so far this requirement has not, the platforms that exist out there on the market right now, I don't think I've seen any that have this feature yet. The third requirement that we wanted to have a near storage, in-storage hardware accelerator. That's why this card was designed to plug into a bigger FPGA over a fast link on which the application acceleration that we wanted to experiment with could be implemented. So we built a small cluster system out of these cards. Each node had 1 terabyte of flash, which consists of 2 of these cards, connecting to a larger FPGA at the time. Now the VC707 is a small FPGA, which connects to the host server just like any other storage device over PCIe. We built, of course, the FPGA also has a small amount of scratch bed memory on the card. And we built a small cluster out of them, 20 machines, connected over regular old Ethernet. And of course, the FPGA accelerators could communicate among them directly using the dedicated storage area network. The first cool part of this system was that because we got rid of a lot of operating system overhead. We got rid of a lot of network stack overhead. When we were talking from storage device to storage device directly, if we wanted an application-specific accelerator on an FPGA talking to any of the pages in the distributed flash array, we could do so at a uniform latency of 100 microseconds, which was very cool at the time because the fastest chip at the time had a latency of something like 75 microseconds, but now chips have become much faster. So this is the photo that we had of the cluster that we had at MIT. The storage device which plugged into the PCIe is what you see on the left. It's very loud and very hot. So it enabled us to do a lot of research. A lot of the earlier papers were on constructing the system itself, but it did enable us to do a lot of application research more recently. Things like flash-based key-value caches, key-value stores. But the application I'll be focusing on today, today's talk, is what's called GraFBoost, on which we try to do graph analytics on this system with near storage acceleration. And this is where we try to solve the second part of the problem, which is the problem of access granularity. Right, solving the second part of the problem from a high level is we introduced a new algorithm for constructing histogram called sort reduce and implemented it as an FPGA in the near storage accelerator. Sort reduce is a low overhead algorithm for transforming a lot of fine-grained read modify writes into a series of sequential read modify writes. And this is one of the aforementioned magic sauces that allowed us to actually get high performance on a flash-based hardware-accelerated analytics platform. And it's applied to a lot of algorithms, but today I'll talk about graph analytics. So graphs. Graphs are interesting. More interesting now, in recent times than even before. Typically, the graphs of interest right now that we can find online are relatively large, hundreds to terabytes to hundreds of terabytes in size, and they're characterized by a very sparse and irregular structure, resulting in a very sparse and irregular fine-grained access patterns, which was a good hurdle for us to try to overcome. So graph access is very irregular typically, because even when the graph vertices are close to each other topographically, typically in terms of memory layout, they can be completely random, as is natural. So if we try to do it naively on storage, the access granularity mismatch kills performance. And another problem is that when we traverse from different set of vertices, even the randomness, the irregularity of accesses is another set of completely independent irregularities. So even if they sometimes have joint neighboring vertices, data size and irregularity limit the effectiveness of caching. So whatever happens, you still get killed by your performance gets killed. So the question was, can we still do graph analytics using this storage-based appliance without requiring us multiple gigabytes, terabytes of DRAM? So in order to solve that, here's a general formulation of an irregular array update in order to explain what the solution looks like. So let's say we have an array X, which is what you see on the right, which is being updated by a stream of update request XS, which we'll see on your left, which consists of key and value pairs, and an update function F. Formulaically, it looks like this. For each index and argument in the update stream, you update the value in X under that index by applying the user-defined function F between the original value in X under IDX and the new argument that came in. And I promise this is the only mathematical formula that I have. So you get random updates because the key distribution in the update stream is random, and it will kill your performance. The first part of the solution is very simple. It's just sort the request. Instead of applying the data updates directly, if you log the entirety of the update stream and then sort it, then we get completely sequential updates. And this is a simple enough idea, but it is still much, much better than just trying to do naive updates into storage because we don't suffer that 1,000-fold performance degradation. But the thing is, because when we have terabyte scale graphs, then we do have terabyte scale logs that we have to sort. And that's also a significant performance overhead if we compare against the fully in-memory implementations, which we are trying to beat. Right. So that's where the second part of the solution comes in, which is reduction, which is the second word in the algorithm sort reduce. So if the update function f is associative, for example, if addition is associative, then the update function can be applied in place whenever we see a key collision in the update stream without having to wait until the whole stream is sorted. For example, here's just some random data I filled in into a stream that is already pre-sorted into chunks of 2. Say we continue to do merge sort. And every time we discover keys that match, we can just apply the update function f directly in place, which results in reduced overhead in terms of the amount of data that needs to be written back, in terms of the amount of data that needs to be read back out. And this continues with every step of the merge sort algorithm, which actually results in a significant amount of reduced overhead. And when we apply this algorithm to various kinds of algorithms, various kinds of graphs, in the overhead saving of the algorithm was quite significant. And at least in one real-world graph, which is the Web Data Commons web crawl graph, the reduction operation managed to reduce the size of the update log that needs to be written back to Flash, was reduced by over 90% before it had to be written to Flash for the very first time, just after the in-memory sort stage. And the similar patterns followed for most of the other graphs that we've tested. So we know that it's at least for graphs, it works fairly well. And to further reduce the overhead of this newly added sort and reduce stage, we implemented the algorithm inside on the near storage FPGA. There's a lot of things interesting that go in. It reduced data movement because it doesn't have to go all the way to CPU, and it reduced cost of deployment of this FPGA as well. And there's a lot of things that go internally to this system, things like the accelerator-aware flash management, file system, merge sorter implemented inside the hardware, the multi-rate aggregator, et cetera, et cetera. But I don't think I'll have time to talk about all of that right now. So I'll just say that there's a neighbor traversal core that traverses the graph structure inside the accelerator itself. And the edge weight and the vertex value comes from each of its locations. And the update log is pushed into the sort reduce accelerator, which uses the amount of memory it has on the board to do as much in-memory sorting as possible. After that, it goes into external merge sort loops that autonomously uses the flash storage that it has locally. Simple enough algorithm, and it was implemented on the BlueDBM device that I mentioned earlier. So in order to evaluate the performance of the thing that we've built, we compared ourselves against the class of other graph analytics applications that was available at the time. They come in three different classes. The one on the left is an in-memory algorithm, GraphLab. The one in the middle is semi-external, which stores the algorithmic vertex data in memory, but it still accesses the graph structure itself, which is significantly larger in storage. And a completely external application, which doesn't require any DRAM. It just uses the amount of DRAM that you have. If you don't have that many, you'll suffer a graceful loss of performance. The two systems that we've built to compare against are called GraphSoft and GraFBoost. GraphSoft stands for the completely software implementation of the platform, including the sort-reduce algorithm. GraFBoost is the one that uses the near storage FPGA accelerator to implement this algorithm. So the evaluation platform that we used is a measly desktop-powered machine. It's a 4-core i5 machine with 4 gigabytes of DRAM. It cost $500 for us to buy it off Amazon. It was augmented with a BlueDBM card. It has a Vertex 7 FPGA, 1 gigabyte onboard DRAM, 1 terabyte onboard flash. Of course, the cost of this thing is kind of difficult to gauge because we built it from ground up. It's expensive. But if we were to say someone were to actually manufacture this, Samsung, for example, would manufacture this, at the time, we gave it a guess of something like $1,500. I don't know if that's completely true or not. We just added the performance of cost of FPGA chips, cost of flash chips, and some margins. So we tested against multiple graphs, but the graphs of interest include the Web Data Commons web crawl graph, which was 2 terabytes in size, 3 billion vertices, 128 billion edges, and the synthetic Kronecker graph, which is smaller in size, half a terabyte, but it has more vertices and less edges. They're kind of a different characteristics. So we evaluate the performance. GraFBoost, when we did breadth-first search on the Web Data Commons graph, web crawl graph, took a certain amount of time to run the algorithm. And the other graphs, other systems, GraphLab ran out of memory, FlashGraph ran out of memory, Xtreme ran out of memory, GraphQi took, I think, 4 days before we killed the software. Of course, this is not a fair comparison, because we used FPGAs and they just, they had an FPGA, they didn't know how to use it. So we constructed a different evaluation. We still have the same machine, which adds up, we're guessing adds up into $2,000, about $2,000 the cost. We compare it against a much costlier machine, which has more memory and more DRAM, 16-core, 32-thread Xeon, 128 gigabytes of DRAM, and 5 half a terabyte PCIe flash storage devices. These were last gen, so I think in total they gave us about 6 gigabytes per second of throughput across the 5 cards, as opposed to BlueDBM, which gave us something like 2 gigabytes per second. So even then, even in terms of flash performance, there was a difference. And there's a third, and this machine cost us about $9,000 to buy at the time. And there was a third system, which is a 5-node cluster, adds up into 60 cores, 128 threads of Xeon processing, and 240 gigabytes of DRAM in total. This cost us a little bit more money to buy, but it was required because GraphLab, the completely in-memory system, required that much money to run. Required that much memory to run anything. So let's look at the results for these numbers. So first is the scale 32 Kronecker graph, which is the smaller of the 2 large graphs, but it has more vertices. GraphLab still runs out of memory. FlashGraph runs out of memory. GraphQi did not finish again. And of the 2 systems that finished, well, of course, actually 3, including the software implementation of GraFBoost, which serves as the one for which all the performance was normalized. We tested 3 algorithms, PageRank, breadth-first search, and between the centrality. The 2 systems that finished, Xtreme and GraFBoost, Xtreme did pretty well for, well, no, actually, we did better than anyone. So that was very cool, considering the cost differential and everything. So let's look at the other graph. The other graph, the Web Data Commons graph, which is larger but has less vertices. GraphLab again ran out of memory. GraphQi also did not finish, but this time the 2 semi-external systems did manage to get some results. The, I think it's, yeah, for the same algorithms, the dark green is Xtreme as before. The light green is FlashGraph. And Xtreme this time managed to finish in PageRank, but did not finish in the other 2 algorithms. The other system did do well in most of the algorithms, but only for one of these 2 graphs that we've tested. And only GraFBoost succeeds in processing both graphs, according to, at least in our results. And what's interesting is that this is not at the limit of GraFBoost capacity right now. As the graph becomes larger, GraFBoost will suffer a graceful descent of performance, but we can still process larger and larger graphs with no problem. But it would not have been a very interesting result to show if it was just GraFBoost showing numbers and everyone running out of memory, so here we are. So in performance-wise, at least from a high level, we showed that even with the lower cost machine with FPGAs and Flash being used in a sort of a smart way, we do manage to get similar or higher performance compared to the software systems that runs on much costlier machine. So before we get to the resource utilization, so even with the 5-node cluster machine, which cost us a significant amount of money, the in-memory system did not manage to get any performance in the larger graph. So we reduced the sizes of the graph until it could actually fit on the 5-node cluster, which was when we, at the scale 28 Kronecker graph, which is 0.3 billion vertices, order of magnitude smaller than the other graphs that we've tested. So for PageRank, it actually does very well. The yellow line is the in-memory processing. It does almost 5 times faster, more than 5 times faster than the software implementation of GraFBoost, which is understandable, which is, good considering the machine actually costs 5 times as more. But the the interesting part is for breadth-first search, the performance actually becomes much worse. And this is, according to our profile, this is because of the distribution overhead having to, PageRank has a very regular access pattern, at least the first phase of PageRank did. But as we get into more irregular accesses, the networking overhead becomes the problem and the performance plummets. So that was also a very interesting result. So in terms of resource usage, using FPGAs within near storage processing actually does buy us a lot of resource reduction. In terms of what's on the left is DRAM usage. The conventional algorithm systems that we've tested required, at least on the system that we run, at least 80 gigabytes of memory to deal with the kind of graphs that we dealt with. Compared to that, because we were doing fully external out-of-core analytics using flash storage, we managed to reduce the DRAM capacity down to 2 gigabytes. In terms of processor thread counts that's required to get performance, the conventional system was using the total 32 threads on the system that we had to get the performance that we did, as opposed to GraFBoost, the GraphSoft actually, the software implementation of GraphSoft, which only requires 16 threads because it was waiting for flash most of the time. But with hardware acceleration, most of the heavy lifting has been offloaded to the FPGA, which brought us down to 2 threads. So very big difference here. The last is in terms of power consumption. The 720 watts was the power consumption numbers of the 5-node cluster, which was completely running in-memory algorithms. But once we went to semi-external algorithms, existing semi-external algorithms, which used flash in a slightly smarter way, even conventional systems' power consumption dropped down significantly. But even compared to that, because most of the processing has been offloaded to the FPGA, the power consumption numbers of GraFBoost was actually, again, significantly smaller than conventional systems. But this is not the whole story, because the server, the PC that we plugged the BlueDBM device into, most of the resources were being idle all of the time, because we did mention that it had 4 cores. It had 4 gigabytes of memory, of which we're only using the 2 threads and the 2 cores. So if we were to use manage to use an embedded system, let's say with 30 watts of power consumption, we would be able to bring down the power consumption of the graph analytic systems even more significantly. And even this is not the whole story. The BlueDBM system that we've built is absolutely not optimized for power consumption because it was an academic prototype. If we were to swap out the numbers with the raw power consumption of the chip, the power consumption of actually manufactured flash storage device, the power numbers becomes even lower, to the point that we are seeing orders of magnitude resource utilization reduction across all metrics, which was very cool for us to see. So that's the results that we've got from that project. So I guess I'd like to spend a little bit of time on the goals that we want to go into after this. The short-term goal, one of the biggest short-term goals that we have is to go in to construct a next-generation platform to do research on. BlueDBM was a custom design. We had to design the PCB. We had to design the interface to the host, block device drivers, et cetera. So it's has been very difficult for us to disseminate results that we got from the BlueDBM platform. And on top of that, the batch of devices that we built, which had the original flash chips, after a lot of erase write cycles, they are aging and a lot of them are dying out. And also the newer SSDs and FPGAs are much faster. So it would be great to build something new, or if we can find a off-the-shelf device that does something like it would be great to move to that. And of course, the more exciting thing is more applications. Right now we're looking at things like bioinformatics, in which we try to do personalized genomics at scale on the same PC class machines. Some scientific computing applications, machine learning, and of course more graph analytics, in which we try to focus into more specific applications like log analysis for security applications, and more. We're always branching out. So these were the short-term goals that we have. And in terms of the midterm goal, once some of the applications are handled, we would like to go into exploring models for effectively using computational storage, which is interesting for us because discovering the right abstractions and interfaces for programming these systems are going to be one of the key factors in making this available to, I guess, the masses. In graph analytics, identifying and exploiting the associativity restriction made sort reduce possible. And I'm guessing something, magic sauces like this would exist across a whole strew of problems. And maybe if we identify a library of those things that can be applied in total to a majority of the problems that we want to deal with, then maybe we can come up with something like a MapReduce type platform on which anything can be programmed by someone who is not familiar with any of this. So in terms of scientific discovery, it seems to follow always this process in which we start with a very simplified model understanding of the world, we go into a very complex model, and then after which we sort of know the nooks and crannies of everything, we manage to come back into a very simplified model which is more accurate. So I guess in terms of exploring more application, in terms of trying to find these more secret sauces, I guess I'm at this point right now. So I guess the midterm goal is to move on to that direction on which I'll be able to build something more general. And of course, the very long-term goal that I have, multiple years, decades maybe, goal that I have, would be to take a rack, take a room full of expensive machines and replace that with a much cheaper one, so that maybe something like an exascale machine can be replaced with something like BlueDBM's cluster. And maybe all of this exascale processing can be powered by that. So I think I may have finished a little bit early, but that is actually all of the talk that I prepared today. And if you have any questions, I'd be happy to take them.